everybody. Welcome to the last day of the winter school. I hope you are not tired until now, and also I would like to thank the organizer of the winter school, especially Karim Bagheri, Hadi Soleimani, and Shahram Khazai for organizing this school. Okay. The lecturer of this session is Ciprien De Saint Guilhem, and the topic of his lecture is multi-party computation. Thus, I have an introduction to the lecturer of this session. Ciprien is an postdoctoral fellow with the ISC Research group at the KU Leuven, Belgium, where he researches multi-party computation-based zero-knowledge proof system and their provable post-quantum security. He obtained his PhD in 2020 from the University of Bristol after moving to Kasich in 2018. He has published work on authenticated key exchange protocol, isogeny-based encryption and oblivious transfer, as well as multi-party computation in the head zero-knowledge proof system and digital signature. Thank you, Ciprien, for accepting our invitation to have a presentation. I pass the session to you. Please sit. Thank you very much.
Thanks for the introduction. And first, let me say thank you, for the introduction, the invitation to speak today. Do interrupt me at any time if there's any technical problem, and we'll do that quickly. So today I'm going to speak about essentially my recent research in the last couple of years, which is the MPC-in-the-Head framework and the Limbo protocol. So it's quite a recent framework of designing zero-knowledge proof systems, and we've done quite a bit of research on constructing schemes for this framework at KU Leuven. So today I'm going to introduce the framework to you guys. And little bit by little bit, we're going to make our way to the Limbo protocol. So I'm going to introduce some intermediary protocols as well, and show you how the design of these protocols has evolved over the last few years. So for this talk, it's going to be in 3 parts. And first, I'm going to spend some time presenting how we can construct a non-interactive zero-knowledge proof of knowledge from MPC-in-the-Head with pre-processing. So if I'm not mistaken, you've already had some lectures about zero-knowledge proofs. What does it mean for them to be, for example, non-interactive, and these kind of things. You've also had lectures about MPC, and this framework is a way of constructing proofs from MPC. And hopefully we can hope that the security features of MPC protocol can help us accomplish the security requirements of zero-knowledge proofs. And in particular, you've also probably heard about MPC in the pre-processing model, for example, the speeds protocol. So I'll be talking a bit about how this also helps us build better MPC-in-the-Head schemes. So once we've gone through the concepts and how it works on a sort of a theoretical basis, I'm going to talk about 4 protocols, 4 schemes, namely Picnic, Barbecue, Banquet, and Limbo. And I've divided these 4 schemes into 2 parts. The first was the MPC-in-the-Head in the kind of the first proposals, which was based on circuit computation. And here I'll talk about Picnic and Barbecue. And in the second part, I'll talk about the schemes that are based on circuit verification. And I'll explain at the time what I mean by the difference between circuit computation and circuit verification. And there I'll talk about Banquet and eventually Limbo. So so let's get started with MPC-in-the-Head with pre-processing. So we want to build zero-knowledge proofs, and we want to build them from MPC protocols. So as is usual for zero-knowledge proofs, we have an arbitrary NP relation R. And we have a public statement X for this relation, and the prover P knows a private witness W for this relation. And this prover wants to convince the verifier that the relation is true, so that W is a valid witness for X, without revealing W. So this is the standard zero-knowledge proof sort of problem statement. Now, in 2007, Ishai, and others had the idea of using multi-party computation. And in multi-party computation, usually there is a function that has to be evaluated in private or in a secure way. And in our case, the function we're going to want to evaluate is the function that verifies the witness. So you see that the function here is parameterized by the statement, and it takes the witness's input, and it should evaluate to 1 if the witness is valid, and 0, for example, if it's not. And because R will be an NP relation, right, this function should be polynomial time. That is the definition of NP. We can check witnesses in polynomial time. So we can, there will always be a multi-party protocol to compute this function f. Now the twist in this idea is that the execution of this MPC computation of f will be simulated by the prover in their head, and it will be checked by the verifier. So the verifier doesn't participate in the computation of the function, but it simply verifies that it's done correctly. And the hope, and of course this is proven and we're going to work through it, is that by doing it in this way, we can achieve the security of zero-knowledge proofs, which is namely soundness, the prover cannot cheat, and zero knowledge, the verifier cannot obtain information about the witness. So let's see how this works. What does it mean for the prover P to simulate multi-party computation in the head? So this is what happens in the prover's head before the zero-knowledge protocol begins, or at the beginning of the zero-knowledge protocol. It's going to simulate several servers or parties. So in my example, I've chosen 3, but it can be more. And these simulated servers, they're the ones who are going to be doing the MPC computation. So the prover has the witness, it will give it to the servers, they will run the computation, and they will output the result of the function, which should be 1 if the witness is valid. But the point is that during this execution of the MPC, the prover can record what is happening. It can record the view of each of these servers into these transcripts that we have on the side. So each server will have a seed, which generates the randomness. It will have a share of the witness. So here I've chosen additive secret sharing to represent the shares, but in theory you can choose any kind of sharing you want. In this talk, however, we'll be focusing on additive secret sharing. And it will also contain the messages that were exchanged during this computation. Now, if I am server 1 and I know my seed and my witness share, I can compute my outgoing messages, the messages that I send to everybody else. But in order to continue my computation, I need to know what I receive. So these transcripts contain the messages that are received by the party. So these are the messages received by party 1, these are the messages received by party 2, and these are the ones received by party 3. Because all the ones that are sent can be recomputed from these values, so we don't need to record them. Okay, so that's the simulation of the MPC in the head. How do we now make a zero-knowledge proof from this? Well, the prover has these transcripts, and it's going to commit to them. So you notice we have a commitment challenge response. So we have a Sigma protocol, actually. The prover is going to commit to the 3 transcripts, and the verifier is going to select, in my example, I have 1 and 3. What this means is that the prover now has to reveal the transcripts for party 1 and party 3. In theory, there can be many more parties, and the challenge can be any subset of these parties. But in the rest of the presentation, and I'll argue a bit more why, we're always going to suppose that the verifier asks for all of the parties except for one. So in this case, party 2 remains hidden, and party 1 and party 3 are opened. So then the verifier has to run a checking phase. Because what does the verifier want to know? The verifier wants to know whether the witness is valid. So the first check that the verifier is going to do is that this output of the MPC computation is equal to 1, that the parties that are open here agree that this output is equal to 1. And the second thing is it's going to check that the prover did not cheat during the MPC execution. Because what can happen is when the prover is recording those transcripts, it can actually cheat and record the wrong messages. It can record messages such that it changes the output of the MPC protocol into an accepting output of 1. But that means that these cheating messages are not consistent. So for example, if the prover cheats on a message that party 1 receives from party 3, when the verifier recomputes the transcript of party 3, it will compute a message that needs to be sent to party 1, and it will observe, because it has got both transcripts, that party 1's message is incorrect. And so if it observes any incorrect messages like this, it can deduce that the prover cheated during the MPC execution, and it will therefore reject the proof. So these are the two checks that the verifier has to conduct. One, that the output of the MPC protocol is correct, and two, that the consistency between the views is also correct. Now, of course, this verifier here cannot see the messages of party 2 because they were not opened. So if there was any cheating in the messages received by party 2, it cannot detect this in this situation. And so the prover has a chance of getting away with cheating. But we will see a little bit later that this probability should be quite low, and there are ways of making it even lower. So this is how we get a Sigma protocol from MPC-in-the-Head. We generate transcripts of an MPC execution, we commit to them, the verifier asks to see a subset of these transcripts, and once it has received this subset, it can check that the MPC execution was correct, and it produced the correct output. So now, whenever we have an MPC protocol to compute any NP verification function, we can have a proof of knowledge for any NP language. So it's a very, very flexible framework. It allows to build proofs for many relations. Now, of course, there is always the question of efficiency, and this is what we're going to look into more detail as well with the protocols we're going to describe. I'm not going to get into much detail during these slides, but because this is a Sigma protocol in its most generic form, it can, of course, be transformed into a non-interactive proof using the Fiat-Shamir transform. So what does this mean is that we take the 3 commitments that the prover generated, we insert them into a hash function, and this hash function produces the challenge. And so when the prover has done this challenge generation, it can send a single proof which contains the commitments, and the verifier can hash those commitments again to obtain the challenge, which is indeed transcripts 1 and 3, and then it can run the same checks that it would run in the interactive version of the protocol. So because it has this simple form of a Sigma protocol, and it can be made non-interactive. MPC-in-the-Head is not only a strong candidate for proving an arbitrary relation, it's also a good candidate for constructing a signature scheme, because non-interactive proof makes for a very easy transformation to a signature scheme. And indeed, in the schemes I will present, their primary application has been to construct fast and short signature schemes. So now that we have the general concept, general idea of how do we construct an MPC-in-the-Head proof, we can talk a little bit about the actual security arguments. First, we need to check for correctness. And as long as the MPC protocol that computes the function is correct, so the MPC protocol does not make mistakes, and the prover is honest, then the output of the function in the head execution will be 1, and the verifier will accept. Soundness, I've already talked about this a little bit. If the output should not be 1, because the witness is wrong, but the parties that are open show that the output is 1, then the prover must have cheated during the MPC protocol to change the output. And if we assume that the commitment is binding, the prover must cheat before the commitment is computed, which means that once it knows the challenge, it cannot change the party on which it cheated. So that means that the prover must guess the party that is going to be hidden by the challenge before it can actually see the challenge. So that means we have a soundness error of 1 over the number of parties. In the previous protocol here, I was saying that if the prover cheated on party 2, the verifier cannot see this. But the prover only has a 1 in 3 chances of cheating on party 2 without being discovered. In practice, we'll use a number of parties that can be as small as 2 and as large as 64, or maybe even 128 or 256. A very large number of parties will mean that this soundness error is quite small, which is good. However, it means that the prover has to simulate 128 or 256 parties in its head, and that's a lot of computational work. So here we have a trade-off in the parameter space of MPC-in-the-Head proof systems. We can have poor soundness error, 1 over 2, 1 over 4, for example, but very fast computation, or we can have much smaller soundness error with slower computation. And I'll talk about a little bit how we can make this cryptographically small, because of course even 1 over 256 is not good enough to make a cryptographically secure proof system. Then finally, we must also have zero knowledge. So the first requirement for this is that the commitment must be hiding. I'm not specifying whether the commitment has to be statistically binding or computationally binding. This can be left as a design choice. So if we want, for example, statistical zero knowledge, we need at least statistically hiding commitments. But this is a choice. And second, the verifier will see n-1 transcript. So in my slides, I'm assuming that, like I said, we reveal all except for 1 transcript of the MPC protocol. So that means that this protocol must be n-1 private. And I used additive secret sharing in my example also because additive secret sharing is an excellent n-1 private secret sharing scheme. And it also has other advantages that I will be talking about afterwards. So in terms of designing very efficient MPC-in-the-Head protocols, this is what has been done a lot in the past. Now there are also some proposals that use Shamir secret sharing, for example, which is no longer full threshold or n-1 private. But I won't be talking about these today. Okay, Yes, and the other option, so here this is an argument about soundness, but because we also want it to be a proof of knowledge, we also need to think a bit about special soundness. And in fact, here we've got a similar extraction strategy that we have for regular Sigma protocols, which is that if the prover has committed to 3 transcripts, and we can and opened, for example, transcripts 1 and 3, we can rewind and ask it to open transcripts 2 and 3. And by assumption, we assume that these are also a valid answer, the verifier accepts. Then, because the commitment is binding, we know that party 2 that was open in the second transcript, in the second execution, is the same as the party 2 that was hidden in the first execution. So then if we take this party 2 from the first execution, we have parties 1, 2, and 3 that are now open. And this means we can reconstruct the witness that was secret shared between the 3 parties. And because we have reconstructed the witness, we can extract it like this. So this is how we can argue special soundness as well for MPC-in-the-Head proof systems. So in practice, there can be some optimizations. I'm going to mention some of them. There are many more. First of all, increasing the number of parties is not a problem for the commitment phase in terms of size, because we can compress many commitments with a hash tree and send only a 1 hash value when we send the commitments in the first round. So here, having many parties does not have a big impact on the proof size, even though it will have a big impact on the computational time of the prover. Like I was saying, 1/n is not secure, but because this is a Sigma protocol, we can repeat the protocol several times, and this will increase the soundness exponentially until we achieve a secure enough parameters. Finally, opening all but 1 transcripts can use a lot of data, and that will make a large proof, and we don't want that because we want digital signatures to be quite short in practice. And so here we're going to focus on MPC protocols that are in the broadcast model. And that means that the messages that party 1 receives and the messages that party 3 receives are going to be the same, because in the broadcast model, every message sent is received by every party in the same way. So instead of having, in this case, 2 transcripts, we only need to give what server 2 would output, because both party 1 and party 3 receive the same messages from party 2. And if party 1 and party 3 also broadcast messages, the verifier can compute these based on the seeds and the history of the protocol. So we don't even need to send what party 1 and party 3 would output. So by doing MPC in the broadcast model, we lose a factor of n in the proof size, because we only need to reveal one party's outgoing messages, which is still where the prover can cheat. Can lie about what party 2 is sending, but that doesn't change. Okay, so I'll just do a quick check that everything is still okay, and okay, then let's move on. And so up until now, I was talking about just any MPC protocol that was kind of from beginning to the end. The parties execute on the input until they get to the output. The issue is, even though we only care about semi-honest secure protocols, right? Because the only security property about the MPC that we care about is the privacy for the zero knowledge. These are not always the most these are not always the most efficient protocols. And some MPC protocols, like you've seen, for example, the Speeds protocol, use a pre-processing and online phase. In the pre-processing, the parties together generate correlated randomness, which is input independent. So it can be generated in advance in very efficient ways, in batching, but sometimes it still needs a lot of communication. For example, in speeds, we need to compute multiplication on private data, so it can involve FHE operations or it can involve OT operation, and that's a lot of communication between parties. In the online phase, then we can use this pre-processing and have very low communication during our input dependent computation. So we pay a high price to generate the correlated randomness, but that means we pay a very low price in communication in the online phase, which is what makes speeds a very efficient protocol. This technique can also be used for MPC-in-the-Head, but here we have a great advantage. The correlated randomness can be generated without all the communication required for the pre-processing. Because if you imagine the three parties are generating the pre-processing, they will generate random values, and then they need to compute some correlated randomness about their random values. But the prover is simulating the MPC, so the prover kind of looks at the three parties from above, and the prover can already see what the correlated randomness needs to be. So the parties don't have to compute it themselves. The prover can just look at their randomness and say, this is the correlated randomness you need. And so by adding this auxiliary information, and this is why we call it aux here, by adding this auxiliary information into the pre-processing phase, there is no communication that the parties need to have with each other. They simply need to generate their randomness and receive the auxiliary information from the prover. Well, I mean, I say they receive it from the prover, but all of this is happening inside the prover's head. So there is no involvement from the verifier yet. Now, while this happens, the prover can choose, it can potentially cheat on the correlated randomness that it will give the auxiliary information about. And if the prover cheats on the correlated randomness, it can influence the output of the MPC protocol. So we don't want this. So we need to come up with a way of letting the verifier make sure the prover is not cheating. So before we were saying the verifier can make sure the prover is not cheating on the MPC online phase because it will ask to see some of the parties. But because pre-processing is input independent, we can do better. And we do this by the prover generates many pre-processing executions, maybe 200 or more. And it will commit to all of these. And that's expensive to compute, but the commitments can be compressed. And so it's not too expensive to send. And then now the verifier is going to say, I want you to show me the entire pre-processing execution for 90% of these executions that you committed to. And this is what we call cut and choose. The verifier will see those 90%. The prover will completely open them because they are input independent, so they do not have any secrets related to the witness. But they contain the aux that the prover computed for each of these executions. So the verifier can recompute these pre-processing executions and check that the auxiliary information that the prover committed to is indeed correct. And so if the verifier sees that the prover was honest for a random 90% selection of the execution, it has a high probability that the remaining 10% that is still hidden are also correct. Of course, there is a small chance that P decided to cheat on 1% of the executions and that these were hidden in the random 10%. But that probability is quite small. And so when the prover reveals, it only has to reveal the master seed, which it used to generate the entire pre-processing execution, and the correlated randomness, that is the aux information. So it's not very expensive to open either. Now the prover is left with 10% of the pre-processing executions. The verifier believes that these are correct. And so now the prover can simulate and commit to the online executions using those hidden 10% of pre-processing. And now the verifier is going to challenge and observe all but one parties, as it did before, and verify the computation, that the circuit outputs 1 in the correct way and that there is no cheating on the communication between the parties. And this phase now uses a lot less data than before because the online phase is cheap, given that we have the pre-processing execution. So at the cost of an extra round of interaction between the prover and the verifier, because now the prover commits to the pre-processing, the verifier challenges the pre-processing, and then the prover commits to the online, the verifier challenges the online, and finally the prover opens the online. So we have 5 rounds of interaction. We have a lot less communication. The length of the messages between the prover and the verifier is much smaller. One thing to note, we can still make this protocol non-interactive, and we can do this in 2 different ways. The first is to use a 5-round version of the Fiat-Shamir transform, which requires a bit of special analysis, but it still works. Or this protocol can be compressed to 3 rounds as well. But I will let you see the references at the end of the slides. And so for these kind of implementation details about transforming to non-interactive schemes and digital signatures, I will let you look into the references some more as well. And of course, you're welcome to send me an email later if you have any question about these things. Okay, so maybe you can take a short break if there are any questions already before we get into the detail of the protocols I want to talk about. Or we can leave all questions to the end. That's also fine for me. I see Karim has... Yes, go ahead.
Is there any question from audience? No. Okay, then that's great. Hopefully that's because what I'm saying makes sense. So then let's talk about some schemes. So I want to begin with 2 schemes, picnic and barbecue. Both of these schemes are what I call in the circuit computation model. And this is probably what you're expecting, which means the MPC protocol computes the circuit that we are trying to prove. And only later we're going to talk about circuit verification, and I'll explain at the time what this means. So here I want to talk about 2 schemes. And I'm going to talk more about the MPC that is used to generate, to create those MPC-in-the-Head schemes. And I'm going to emphasize why choosing either, for example, binary computation or arithmetic computation can bring sort of different advantages for an MPC-in-the-Head proof. Picnic is perhaps the flagship, as in like the most well-known MPC-in-the-Head scheme, because it was submitted to the NIST post-quantum digital signature competition. It has survived all the way until the final round. And even when other schemes were standardized by the NIST, it remained as an alternate candidate. So, and it was also very strongly optimized during this time. So it's actually even though it was one of the first schemes to be proposed, and it maybe didn't benefit from
some of the more theoretical advancements of MPC-in-the-Head that came afterwards, it was also studied in very great detail and optimized at a very low level, and it's a very, very fast scheme. The barbecue scheme was an alternative to Picnic that was developed very shortly after Picnic was proposed. And when it comes to it, I will explain what exactly the difference was between the two. So first, let's get into Picnic. And the particularity amongst the schemes I'm going to talk about for the Picnic scheme is that it uses a binary computation protocol for MPC. So in the case of, here's some of the references, by the way, if you want to check it out later. So we're going to represent this function f of x as a binary circuit that we call C. And this binary circuit has wires and gates between those wires. And in this case, the gates are XOR gates, which are basically plus gates, and AND gates, which are multiplication gates in some ways. Now, for each wire on the circuit, there is going to be, once we put the witness in the circuit, all the wires will take a certain value. And of course, this is the value that we want to keep hidden, because revealing the internal wire values will reveal information about the witness. So when there is a real value Z on a wire of the circuit, the protocol will also have a masked value Z hat, which is computed with Z XORed with a random mask lambda. So the way that the MPC protocol works is that the masked value Z hat will be public because it's masked by a random mask. So this completely hides the real value. And the mask itself will be full threshold secret shared using an XOR secret sharing. So that means every party will hold the public masked value and a share of the mask for each wire. So that's kind of the data structure of the protocol. For each wire, there should be a masked value and a share of the mask that every party has. And the way the MPC protocol works is that the pre-processing will prepare the masks in a special way, and the online phase will begin with the masked values of the input wires and make its way through the circuit, through the XOR and the AND gates, computing each time the masked values of the next wires until we arrive at the output wires, which are revealed. So let's take a look at how the pre-processing works, because that allows us to understand the cost that is added to the proof size, right? Because we care about reducing the proof size, particularly making shorter signatures. And so we need to understand the pre-processing phase to understand the correlated randomness that's required for this MPC protocol. So the first thing we do is every wire needs to have a mask. So the question of the pre-processing is, how do we generate them? So first, for the input wires, the mask is generated completely at random by the parties. Each party has a seed. They generate a random bit that becomes their share of the mask. In this way, we have masks for every input wires. But we also generate random masks for the output wires of the AND gates. So that's it. We have wires for input and AND gates output. For the XOR gates, because XOR sharing is a linear secret sharing, it's quite easy that we should be able to XOR the two masks, and that will give us the mask of the output wire of the XOR gates. This is a local operation that the parties can do locally. They don't need to communicate. So this is free. That means the prover does not need to add extra correlated randomness to make this work. For the AND gate, we have already the random mask for the output wire gamma, but, and it's a little bit intuitive, and I'll explain on the next slide exactly how it works, we also need to know the AND of the two input wires. So for the XOR gates, we needed the XOR of the two wires. For the AND gates, we need the AND of the two wires. Now, this is not a linear operation in MPC, well, in general, for the on this field, so this is not free. So we could imagine that the prover gives every party their share of this product of masks, but there is a better way to do it. What happens is that all the parties except the last one, Pn, will generate their share completely at random. So because this is from their seed, this is free. The prover does not need to add extra information. But the last share, the nth share, has to be defined in this way, because we need to take the real value, that is the AND of the two masks, and we need to subtract from it the addition of all the shares we've already sampled. Because then, when we add all the shares with the nth one, we get the correct result. But the parties in the MPC, they do not know the real value of the product. Only the prover knows this value. So it can look at the shares of the first n-1 parties, look at the value of the product, or the AND, and it can compute this nth share and add it to this auxiliary information. So now, in summary, that means that for every AND gate in the circuit, when we're going through the pre-processing, we need to add 1 bit of information for every AND gate that is in the proof. So now this already gives you an idea. If you have a circuit with a lot of AND gates, this auxiliary information is going to grow linearly in this size. Okay, so now that we have all of the masks, the next step is the online phase. And remember that the online phase in this protocol computes all the masked values. Before we go through this, note that the public, if we want to reconstruct the mask lambda from its shares, every party has to broadcast their share. So we are in the broadcast model that I mentioned was advantageous for MPC-in-the-Head. So the parties begin with the masked values for the inputs. The prover gives them because it knows the input wires for the witness, and the mask is already generated from seed. For each gate in the circuit, the parties will compute the nest masked values in the following way. For the XOR gates, it's easy. They're just added together. You add the two input masked value, you get the output one. Because the two masks were added together, all the arithmetic is still fine. This is local and this is free. There is no communication between the parties. Now for the AND gates, it would be tempted to just compute the masked value as the product of the two masked values, like here. But the problem is when we compute the product of the two masked values, yes, we'll get the product of the two real values underneath, right? But we will also get cross terms. So we will get the mask of beta multiplied by the real value of alpha, the mask of alpha multiplied by the real value of beta, and we will get the product of the two masks also. So this is why the parties need to compute this value S. Now, the Z hats, they're public information, so we can compute the AND with the secret shared information for free because it's a linear secret sharing. So this is a linear operation with a public coefficient. So by adding these two terms, we can cancel out from here, S is added, right? So we can cancel out the two cross terms. Here is where we need to add the product of the masks to cancel out the product of the masks inside this term here. And finally, we need to hide again by adding our random mask gamma. So S can be computed locally in secret shared form, but we need to make S public to be able to add it back to here. And so we do this by reconstructing it, which now costs 1 bit of communication. And we need to open it because the Z hat, here has to be public. It cannot be secret shared. So again, we add another bit of communication per party. So in some, per AND gate, because this is broadcast. So as I said, when we open the parties, we only need to open 1 party's worth of outgoing messages. So in summary, Picnic costs, for every AND gate in the circuit, Picnic costs 1 bit of proof size for the pre-processing and 1 bit of proof size for the online phase. So this is very cheap. We're talking about only 2 bits per AND gate. Of course, the soundness is always 1/n, so we need to repeat that several times. So those 2 bits are multiplied by the number of times we need to repeat. But when we compare MPC-in-the-Head protocols, we usually have to repeat the same amount of time, roughly. So it's okay to just compare if the MPC protocol are very similar, so they use full threshold secret sharing, broadcast communication, processing, pre-processing and online phase. It's okay to just compare the communication at the lower level to get a rough idea like this. So this is the MPC scheme behind Picnic. To then obtain a signature scheme from Picnic, it's very easy. We prove knowledge of the key to a block cipher. So there will be a public plain text and a public ciphertext, and the MPC-in-the-Head will simply prove that it will prove knowledge of the key to the block cipher that maps the plain text to the ciphertext. And because a block cipher is a symmetric key construction, and MPC-in-the-Head has no computational assumption, because full threshold secret sharing is statistically secure, or perfectly secure even, and the soundness is simply 1/n. There's no this means that we have a very naturally post-quantum scheme if we prove security in a quantum safe model of security, such as the QROM, for example. So for Picnic, the choice of block cipher was LowMC. And LowMC is a block cipher that was proposed in 2015, and it is specifically made to be very efficient in MPC. So it has a low number of nonlinear AND gates. And the issue with the LowMC block cipher is that it's quite new. And there's nothing wrong with it being new, but it just means that it's not as secure as, for example, AES. Because AES is a block cipher that has been around for a very long time. Many people have tried to attack AES, and none of them have succeeded, as far as we know. And so the confidence of AES as a block cipher is higher than of LowMC. So when we started thinking about, okay, what can we do with MPC-in-the-Head, we thought, well, Picnic is good. It's efficient, LowMC is fast, but it's not as trusted and maybe not as secure as AES. So when we first proposed the barbecue scheme, we were like, our question was essentially, can we do Picnic but with AES? So before I talk about the MPC behind the barbecue scheme, I just want to talk a little bit about the AES algorithm, because maybe not all of you know exactly how it works, and I'm not going to describe it in great detail. But for the short description, AES is a 128-bit state block cipher with a key length that can change. And on this 16-byte state, each round, 4 operations are applied. So there can be about, so anywhere between sort of 8 to 10 rounds. No, sorry, 10 to 14 rounds. And each round is a repeat of these same 4 operations. So the first operation is we simply add a round key to the entire state. That's just an XOR, that's linear, so it's very easy to do in MPC. Then we have a substitution layer, because AES is a substitution permutation block cipher. So here each byte of the state is replaced by another one, according to the AES S-box. And that's a highly nonlinear component. It's because there is no linear operation that says how each byte should be replaced by another. So this is the part that we're going to focus on. Then there is some shuffling, the shift rows and the mixed column operation, and that's just moving bytes around. So for MPC, it's also no problem. So now the S-box is where we focus. In short summary, the sub-bytes operation applies the following function, which takes the input S and inverts it if you consider computation over the field F2 to the 8th. And if it's 0, it maps to 0. And then there is also a public affine transformation, but because it's affine, it's linear, and we don't need to focus on it for the purpose of this talk. Now, this inverse operation, the best way we have of computing it, costs 32 AND gates. 32 AND gates, if we use the picnic binary MPC protocol, that will cost us 64 bits of proof size for each S-box. Okay, so that's quite a lot more compared than if you add how many S-boxes there are. The simplest AES 128 has 200 S-boxes. That's quite a lot of data. And low MC is much smaller than this, so it's not ideal. But while this costs 32 AND gates over a field, bits, it costs a single inverse operation over the field. So our idea was like, if we think about about AES in an arithmetic way rather than a binary way, maybe there's something we can do here. But in order to answer this, we first need to know what kind of MPC protocols for arithmetic circuits we can use in MPC-in-the-Head. So this is where, for example, the speeds protocol comes into play. Because what we can do is when we represent our function as an arithmetic circuit C, which has field elements on its wires and addition and multiplication gates, we can propose an MPC protocol that works as follows. Each wire value is additively secret shared between the N parties, very much like speeds. And each party holds only a single share of the wire. We don't have a publicly masked, so there is no mask and masked value. We just have shares of the wire values. And the pre-processing will prepare the shared randomness, like before, and the online phase will compute the addition and multiplication gates. So how the nonlinear part here is the multiplication. So we're going to focus on looking at how does that work, because additive secret sharing is a linear form of secret sharing, and therefore many things are free. Operations with public constants, whether additions or multiplications, and addition between shared values, that's all free. So only the multiplication of x and y to give z will cost pre-processing and communication. So here is where we use the beaver triples or the multiplication triples. So the role of the pre-processing is to generate these triples. And here, the only correlated randomness we need is for the C value, because A and B are completely random. And then once we have this, multiplication proceeds in this way. We hide X with A, and we hide Y with B, and this gives alpha and beta. In step 1, They're still secret shared because this was linear operations, but in step 2, we need to open them with broadcast. So that will cost 2 field elements for the proof size. Then each party can locally compute this Z value, which is alpha times beta, which contains X times Y, but it contains all the cross terms as well that we don't like, right? A times beta, B times alpha. So we remove those cross terms using those middle terms. And because they also contains A times B, oh no, sorry, we've removed A times B too many times now, so we need to add A times B back in with this C value. So in the online phase, these steps 1 to 3, that's the online phase, we're going to cost 2 elements, alpha and beta. And in the pre-processing phase, this is going to cost us 1 element to compute the C value. Because as before, the prover needs to give the nth share to party Pn. So the prover can see what the value of A times B is. The n-1 shares of the previous parties can all be generated from seed, and it's only the last share that needs to be added into the aux component. So now that we can do multiplication, we also want to do inverses, right? Because AES uses inverses, it doesn't use multiplications. So how do we compute an inverse? Well, we take a random input, we take an S-box input S, and we have a random value R, and this is free to generate in MPC-in-the-Head because every party can generate a random share. We first compute the multiplication of S times R. That costs us 3 elements in the proof size. 2 for alpha and beta, and 1 for C. Then we can open this S times R, and that costs us a 4th element in the proof size. And now every party can locally compute the inverse of S, because they can take S times R, they can invert it as public value, and they can multiply it back with the R at the beginning, which leaves only a secret shared value of the inverse of S. So now this costs us 3 elements here, 1 element here. So we have 4 elements. And remember that AES operates over the F2 to the 8 field, so it operates over bytes. So we use 4 bytes of proof size, that means 32 bits. So if we use the picnic MPC protocol to compute AES, we needed 32 AND gates, which each cost 2 bits, so 64 bits. But if we use the arithmetic circuit, we only need 4 times 8 bits, which is 32. So we've halved the cost of each S-box in the MPC-in-the-Head proof simply by looking at the AES operation not as a binary computation, but as an arithmetic computation. So when you want to prove something in MPC-in-the-Head, it's important to consider, is it suitable for a binary circuit, or is it suitable as an arithmetic circuit? Which one is the one that's going to cost me the less proof size? So in this presentation, I'm skipping over some details. For example, if R is 0, this method doesn't work because this will be 0 and it cannot be inverted. If S is 0, there is also a special case. The S-box inversion cannot invert 0S when it is 0. So in our paper, we propose ways to work around that as well. But this is more implementation detail, and I'm not going to expand about it more than this. The important part is this kind of, okay, already switching from binary to arithmetic can help us have savings just by picking an MPC protocol that's better adapted to the circuit we're trying to prove. Okay. So now that we've talked a bit about circuit computation, I want to move on to the topic of MPC-in-the-Head from circuit verification, and giving you a bit more detail about two protocols that are built in this model, namely Banquet, which was, I think, constructed in 2020, and Limbo, which was constructed in 2021. So both of these are quite recent schemes. And this is going to take three parts. So first, I'm going to start a little bit by talking about what I mean by witness extension and verification. And these are ideas that come from sacrificing techniques in MPC. Because in sacrificing, it's usually used to generate random triples. We're going to generate two triples, either of which can be suspicious, they can be malicious, they can be wrong. And we're going to use an operation to sacrifice one of them to verify the other. And if the operation fails, then we know that one of the two triples was wrong. And so what this means is that up until now, the parties in the MPC protocol, they were given this pre-processing data that was completely random, and they were given the inputs to the circuit, and they were computing their way through each of the gates. But instead, what we're going to do is each time the parties come to a multiplication gate, the prover is going to give them the result of the multiplication. So they're going to say, oh, we've got an X and a Y secret shared, and the prover is going to say, here is the not the correlated randomness, but here is the output of the multiplication gate. Please carry on. So the online phase is now completely free, because the parties simply receive the result of the multiplication from the prover. There's no need to compute the circuit anymore. But instead, of course, the prover can cheat when it gives the result of these multiplications. So the witness of the computation is no longer just the input values, it's also all these results of the multiplications. So this is what we mean by witness extension. The witness is given, the input to the circuit is the witness, the original witness, plus all of the multiplication outputs. Or it can be any nonlinear gates, really. But now, because all of these multiplication results are untrusted, they're suspicious, the prover could have lied when it provided them, the MPC parties have to execute a verification protocol. So instead of the online phase being a computation protocol, it's now a verification protocol. And the advantage is that when you're doing a computation protocol, you can only compute the multiplications almost one by one, right? Maybe you can compute a few in parallel if they're in the same level of the circuit, but sometimes you have to wait for the result of previous ones in order to compute the next ones. But when you execute a verification protocol, you already have the entire list of multiplication results ready. And so we can batch them, we can compress them. There's many more clever protocols we can use to do this task more efficiently. So the first way of doing this is the sacrificing technique I was talking about before. So the MPC parties receive these suspicious multiplication results, and they verify them by also receiving a suspicious random triple and doing the sacrificing equation. Now, what's very useful about this is that we no longer require cut and choose. Remember, cut and choose was this method where the prover would commit to many, many pre-processing executions. It could be up to 200 or more. And that's very intensive computational work. And at the end of the day, 90% ended up being wasted because they were just opened to the verifier. So by doing these kind of sacrificing, we only need one triple for every multiplication we're going to use. And this triple doesn't even have to be correct. It can be incorrect, potentially. The point is we're going to check after. So the way this works is we have the Z and the X and the Y inside the alpha and the beta, as before. But we also have this epsilon value, which randomizes the Z, and it's also included in the alpha. And the point is that if Z is not equal to X times Y, then Z minus XY, right, which is included in the Z minus alpha beta, that's not going to be 0. And we're going to test whether it is 0. The role that this epsilon plays is that it randomizes this error, because if the prover knows what the error is, the Z minus XY, if it has cheated on Z. But the verifier will give this epsilon so that the prover cannot predict what the error will be. And the second triple ABC, because we cannot simply reveal X times Y, right? So we need the alpha and beta, so we still need the ABC to help remove the cross terms from alpha and beta. And so this epsilon also has a bit of a randomizing effect on C if there was an error in C. So when the parties compute this V, they need to check whether it's 0 or not. And this, if it is, then we can say that this multiplication has passed the verification and it's accepted as so Z is accepted as a correct result. And if it fails, the prover can abort. So,
excuse me, Ciprien, I had a question. Is it possible to ask now? Just in previous slide.
Yes, of course.
So, I mean, you said witness extension. So is it equal to saying that we just prove the multiplication gates in each circuit? That
well, so witness extension means that the output of the multiplication gates become part of the witness. So because we're proving a circuit that is executed on a witness, we can say, okay, the prover only adds the witness, but then the MPC protocol has to compute all the results, all the gates. Or we can say the circuit simply takes the witness and it also takes as input all the results of the multiplication gates and then checks whether the output is 1 or not. So this is what we mean by...
Yeah, I mean, is it because usually once we want to prove circuit satisfiability, we start to first execute the circuit with the witness, and then we obtain the wire values, additions, and multiplications. But since here you use secret sharing, which is linear, so we know that the addition should be free. So I was thinking before this idea that you mentioned to ask that, do we really need to prove the additions? But now then I see that you exactly do that you don't prove the additions because additions can be done free, I mean, for free locally by verifier as well. So now I'm just curious to know if this is the same intuitively idea that you sort of just, I mean, by injecting, I mean, finally you have to compute, but since you are just single party that you know all of them, so you can inject these multiplications and the outputs are for inputs of these multiplications, but you first need to also do this intermediate additions, I guess. But I guess you skip it because you assume that it's locally computable, if I'm not wrong.
Yes. So indeed, in this slide, I'm not mentioning additions because they're free. So if I was to break it down in a bit more detail, what happens is before the MPC-in-the-Head phase, the prover knows the witness, so it can execute the circuit, in the clear without secret sharing or anything, privately. it can, when it executes the circuit, it records the output of every multiplication gate.
Exactly.
And then it creates this extended witness. And now we move into the MPC-in-the-Head phase. It secret shares the witness, and the parties can start moving through the addition gates locally for free. And when they reach a multiplication gate, instead of computing it using, for example, the speeds method before, they simply take the next multiplication value from the witness. And
Exactly.
they take this as, they accept this to be the result of the multiplication, and they continue through the rest of the circuit, taking new multiplication results from the witness each time.
And you batch and give a one proof for all these multiplications here, yes?
Yes. So at the end, the parties, they arrive at the end, they reveal the output of the circuit, which should be 1.
I see.
And now they need to move to a second phase where they execute a verification protocol for all of the multiplication gates that they trusted in the first part. Yeah.
Okay. And this proof is linear, I guess, yeah, in the number of multiplication gates.
Well, yes, because so it depends what you mean by linear. Which part of it is linear?
So let's say you want to batch this, let's say, n multiplication gates. So your proof should be linear on this end, the number of multiplication gates that you have.
So the proof size has a linear component because the prover has to inject all the multiplication results.
I see.
And this always have to be included. You know, this is usually a correction value, in the same way that we had the aux before.
I got it. Okay, this beaver things. Okay.
Yes, exactly. But the verification protocol itself, and this is where optimizations come from, doesn't have to be linear in the number of multiplications. We can check m multiplications in sublinear communication. But because they had to be injected before, there is still a linear cost to the proof.
I see. Thank you very much.
Yeah. But yeah, so thanks for making me clarify that. So in order to resume a little bit how this verification works, we no longer have cut and choose. But in order to soundly sacrifice triples, because right now we're talking about triple sacrificing, so each multiplication has its own triple, random triple, that is sacrificed to perform the verification. The parties need a random challenge epsilon, and this epsilon has to come from the verifier. And because if the prover knows this epsilon when it is committing to the z's, the output of the multiplication, that can be that's a problem for soundness. So yes, the prover commits to this extended witness, then the verifier can send the challenge, and afterwards the prover still has to commit to the online phase of the verification protocol. So in this case, verification means sacrifice. And so in the previous slide, verification means computing this v-value, which is a linear operation, it's for free, and opening the v-value to check that it's 0. Opening is not for free, but when we open to check that things are 0, we can actually use a linear combination method to compress this. So even though we have m values, because we have a v-value for every multiplication, we can take a random linear combination and open a single result at the end. But we still needed a new triple and an epsilon for each multiplication. But this means that we again have a 5 or more round protocol, and the or more I will explain a little bit later, where the prover will commit to the suspicious data, the suspicious multiplications and the suspicious triples. Then the verifier will send a verification challenge, and now the prover commits to the views of the verification protocol, because there is no longer any view of the computation protocol, as I was just explaining to Karim, because it's now all free. Everything is either linear addition gates or multiplication gates are already in the witness. So there is nothing to do. But it's the verification protocol that we have to commit to. And once that's committed, the verifier can send a party opening challenge, as is usual in MPC-in-the-Head, and the prover will open those selected parties. So MPC-in-the-Head always finishes with, can I see parties 1 and 3? And the prover opens parties 1 and 3 and keeps party 2 hidden. Of course, this is for more parties in practice. But what changes is the rounds before. So this is the framework for a verification-based MPC-in-the-Head protocol. And like I was saying to Karim, there is always this linear cost when we have to inject the multiplication. Just like before in the computation paradigm, we had to pay online phase cost for every multiplication. But now the freedom we have is to improve the verification protocol and make it more efficient. So this is where Banquet was the first protocol that we were proposing to do this. So Banquet is actually a verification of inverses, but I'm going to show you verifying inverses is the same as verifying multiplications. So before, when I was talking about barbecue, remember the cost of a multiplication was 3 elements, but the cost of computing an inverse was 4, because we had to do some extra steps. Now when we want to verify inverses, it's actually the exact same cost as verifying multiplications. So we've already got some gains, because if you want to verify that t is the inverse of s, you simply have to verify that s times t is equal to 1. So it's a multiplication with a fixed outcome. And it's not the result that's suspicious, it's actually the t value, so one of the 2 things that are modified. But that doesn't change anything about the protocol. So in Banquet, the first idea, the naive idea, is the prover injects the inverses, we know this, and for every multiplication tuple ST1, we perform 1 sacrifice operation with triple ABC. Now, this is quite expensive because we have to inject T, which, remember, in barbecue, we didn't have to inject the result of the inverse operation because we were computing it. But here, since we're verifying, we have to inject the result of the inverse. So 1 element for the injection of T, 1 element for the injection of C, because we need C to be correlated with A and B. And if I just go back to this, we also need 1 element for alpha and 1 element for beta when we open them in the sacrificing equation. So the problem is we're still at 4 field elements per inverse gates. This +1 here is the linear combination to check that all the v values are equal to 0 I was talking about. So we haven't actually made any progress. This is the same cost as barbecue, 4 elements per inverse gate. But this is because this is quite a naive protocol, verifying every multiplication with a new triple. And we can do better than that. And the way we're going to do is we're going to use polynomial-based checking. The way this works is we're going to define 2 polynomials, s and t, and you see here they're going to be defined, so we're going to interpolate them, and we're going to define them using our s values and our t values. And note that we can only do this because we know all of the s values and all of the t values. So this is why verification is powerful, because we have all of the inverses ready to be checked. So we define s and we define t in this way, and we define p as the product of s and t. So of course, normally, if the prover is honest, the first m points of p should all be equal to 1. because that is what we expect them to be. If these were multiplications, we would simply have x, y, and p would be defined with the z's instead of the 1s. And then we need to check that these two polynomials are equal, the product of s and t and the p polynomial. And we do this using a random r, and we open these 3 points. So we evaluate p, s, and t at r, and we check that this equality holds true for the evaluation at r. The reason why this works is because of the Schwarz-Zippel lemma over fields, which tells us that if we have a non-zero polynomial and we pick a random point and evaluate that polynomial at that point, the probability that this evaluation is 0 can only be less than the degree of the polynomial divided by the size of the set where we chose our point from. Because a polynomial of degree d over a field has at most d roots, so there are only d points for which the evaluation can be 0. So if the degree is quite small and the size of the set is quite big, this probability is quite low. Now in our case, q is going to be this polynomial p minus s times t. And if the prover is honest, and p is the correct product of s and t, and all the t values are also correct, q should be the 0 polynomial. So this q of r will always be 0. But if the prover cheated, then the probability that this check here passes, in other words, the probability that q of r is 0, is going to be less than this fraction here. Because p is the product of, it should be the product of s times t, so it has degree 2m. And so we have 2m at the top. Now, I just mentioned here that when we open s of r and t of r, this can leak information, so we need to add some random points. But the point is that this is how we improve the protocol. The prover commits to s, which is the inputs of the s boxes, and that's always computed for free, based on when we go through the circuit, that's computed for free. It's only the t values that have to be injected. So we have to inject m values, 1 for each s box or 1 for each multiplication gate. Then we commit to p. Now, when the MPC parties want to compute this polynomial p, they know that the first m values of p have to be 1, or they have to be the z values for multiplications. So the prover doesn't need to give those first m values to the parties. Instead, because p has degree 2m, because it's the product of s and t, the prover has to give the following m points to p. And so when the prover commits to p here, that's another m cost, 1 for each multiplication. Then the MPC parties have to open p of r minus s of r times t of r for a random point r, given by this is the same as the epsilon. It has the same role. It randomizes what we're checking. And so, in conclusion, we have only 2 times the number of multiplication gates. 1 for t, which we cannot remove. We always have to inject them. But now, rather than 1 triple for every, and with the opening of alpha and beta for every multiplication, we simply have the m points that define p. And that's where the second factor comes in. The 4 elements that are added, they're p of r, s of r, and t of r that have to be opened. And they're also, there's an extra point because there's no cut and choose, and there's actually a hidden triple. When I say that we need to add a random point s0, t0, we also need to add p0. And so that gives a fourth element here. But see, by changing the way we check our multiplications, we can greatly reduce this, this factor. Now, I say S is randomized, and that's because we have to randomize the vector, like the multiplications we're checking, to make sure that there's no further cheating. So this adds an extra round of communication, in fact. But for the details of this, I'll let you check the banquet paper. Now, we can go even further. And in some sense, the protocol I've just shown you verifies this inner product. It verifies that the S polynomial multiplied by the T polynomial, defined by these two vectors, are equal to this sum of the random coefficients. So the P kind of represents this sum in some way. But if we instead say, well, we take our number M and we're going to cut it, or we're going to separate it into two factors, we can reduce the size of each of these vectors, and instead have only M1 values in each of them. And this also reduces the size of the P polynomial. And we simply have to check M2 of these copies. So we're going to still have the same number of S and T's, but we're just going to arrange them in M2 different inner products like this, all with the same result. And so by defining M2 copies, what we do is we have M1 polynomials, each with M2 points that define them. And because these two polynomials now have degree M2, and we can sum the M1 of them together, we only have one P. And the degree of this P is now 2 times M2 rather than 2 times M. And M2 is only a factor of M. So the way this works is we commit to S as before and the T's, and this we still have to commit to all the T's. But when the prover commits to P, the degree of P has been reduced, and therefore this commitment costs less. And we always open again, well, here we have to open a bit more points, but that's still a constant number. Sorry, it's not constant because it depends on M1, but usually we can pick M1 to be slightly less than M2, and M2 can be about square root of the size of the circuit. So instead of having 2 times the circuit, we only have the 1 time, which is inside T and we can never remove, plus a square root additive term. So now this is an improvement of the verification protocol. Before, so we started all the way here with a verification protocol that cost us 3 elements per gates. Then we moved to a verification protocol that only cost 1 element per gate, per multiplication gate. And then we moved to a verification protocol that actually only costs square root of the number of multiplication gates. And finally, it's time to talk about Limbo. And in fact, I'm going to say very little about it because you already know most of how it works. Limbo is about doing MPC-in-the-Head, and it's about doing MPC-in-the-Head with circuit verification, where the results of multiplications are injected into the computation. And it's about doing a multiplication verification protocol. It's just about doing it even better than how we did it in Banquet. And so the way you can think about it is that in Banquet, I'm not going to go on this next slide just yet. In Banquet, we started with all our multiplications, and we did sort of one operation to compute this P polynomial. And the thing that changed is just the way we computed the P. But once we had our P, we just opened it and opened like the evaluation of P. And we were checking whether this was equal to S times T or the sum of S times T. So the point is we only had this single compression round from all of our multiplication gates down to a single equation. And the idea behind Limbo is to not compress in a single round, but to compress slightly less and repeat that several times. So instead of checking, we're going to move from checking one inner product that has quite long vectors into checking another inner product that has shorter vectors. And we're going to repeat that. We take the shorter vectors and compress them to even shorter ones, and even shorter ones, until we, like in Banquet, we arrive to just a single x times y equals z or not. So the way this works is we take our randomized x's, which were the same as our randomized s's before. We have m of them. We take all of our y's, and we have this z. That's the inner product tuple we're checking, right? So the inner product of r x with y has to be equal to this z value. This is what we start with at the beginning. Then we cut our inner product here of length m into k inner products of length l. So each vector has length l, same for the b. And now the prover has to help the parties compute the intermediate results of these inner products, because the parties only know some of them. So the prover has to help them compute this. So the parties do that. They compute C1 all the way until CK, technically only CK minus 1, because once you've got all but 1, we can recompute the last from Z. And then we have a Banquet-style compression using polynomials. And I'm not putting the details of the maths on the slides because it would take a bit too much space and would be more confusing than anything. But the idea is, because each of these has dimension L, we can compress them using the polynomial check, and using the challenge from V, evaluate our polynomial, and we essentially have L Banquet checks in parallel in some ways. And we end up with a single inner product which has only length L. So we moved from M to L by dividing by K. And now we have this next inner product tuple of size L with Z prime, and we can take this and again divide by K, and again divide by K, until L is basically equal to 1. And we've reached the same final stage as the Banquet protocol. So for example, if we can do a little bit of mental arithmetic, if we take m to be 2 to the 12, for example, then the Banquet check costs square root of that. So 2 to the 12 square root is 2 to the 6. That's 64, if I'm not mistaken. So we have a cost of 64 for the Banquet check. But now let's take instead k, the Limbo check, and we have k equals 2. Let's say k equals 2. So what's the cost of doing one round of this? Well, we need one element for C1. C2 can be computed using Z and C1. So that's one element. And I know from the Limbo paper that compressing this costs k elements. So another 2, so that's 3. Every time we do this round, we divide by 2. The size, so we had 2 to the 12, and we divide by 2, so we need to do 12 rounds. And each round is going to cost us 3 elements, so that's 36 elements. So Banquet cost us 64, and Limbo only cost us 36. And actually, if we take 2 to the 10, you can see that Banquet would cost 32, and because we have 2 to the 10, we only have 10 rounds for Limbo, 3 elements per round, that's 13. So for 2 to the 10 operations, Limbo costs 30, Banquet costs 32. Not a big saving. But when you go to 2 to the 12, Limbo only goes up to 36, whereas Banquet goes up to 64. And that's because the Limbo check is logarithmic. If we take a logarithm base k of m, and that's how we reduce it. And this is actually even more flexible because k can be anything that you want. You can choose k to optimize or not, because the restriction is that now you need a new round of interaction with the verifier for every compression round. So, sacrificing was already a 5-round protocol. Banquet is actually a 7-round protocol. If we have 2 to the 10 and we take k equals 2, here we have like a more than 10-round protocol. I think it's about 12-round protocol even. So when you have a 12-round zero-knowledge protocol, that becomes a bit difficult to make non-interactive, and it becomes very difficult to analyze, and it has to be taken more carefully. By choosing a different k, we can make this slightly less as well. So the Limbo protocol is in this line of verification-based protocols is the latest and so far the best, although Picnic is still very fast because it uses low MC. But this is, in some sense, the Limbo protocol, just a better multiplication check for MPC-in-the-Head. So that's all I had prepared for today. I was going to say tonight because it's night for me, but it's still daytime for you guys. And I'm happy to take some more questions now.
Thank you, Ciprien, for your presentation. It is very useful for us. Dr. Soleimani has a question. You can ask your question.
I had one question. I don't know if Hadi also had.
I did that.
Please ask your question.
You don't? Okay, I can maybe start, then if Hadi has, can ask after that. So Ciprien, in the last slide that you shared, so you made this verification logarithmic because in a recursive way, so you are dividing, by slots of k. So if k is binary, so you have to open just one. But if k gets larger, you have to open more, I guess, or no? If I'm wrong, or
yes, indeed. So the cost of opening each, the cost of the injections for each round goes up by k as well. So you need k for the compression, and you need k minus 1 for these inner products. So you have a 2k cost, yeah.
And this is the trade-off between the rounds, yeah, because if k is small, the number of rounds goes up. If k is large, I guess, then the number of rounds comes down, but the communication goes up. If I am okay, is it correct?
Well, if k is large, it goes up, but only so much, because you only need to repeat the rounds like a logarithmic number of times. So if you want to prove much larger circuits, so if like 2 to the 15 or 2 to the 20 gates, you could take k is 4, and you'd only have 5 rounds. So you can really play with those parameters. Like, yes, the cost of each compression round goes up if you increase k, but you're also going to have less compression rounds.
Oh,
and so it depends on the...
So basically, k times L should be equal to M, yeah? Because L is each set and k is a number of, okay. So if you have M20, then you want to take 4, and then that will, get 5. Okay, I see.
Yeah.
This is quite nice flexibility that you can have in this MPC-in-the-Head.
Indeed, because if you have k is 4, then you go from 2 to the 20 down to 2 to the 5, right? Is that what I'm... And then, like, if you again divide by... No, No, sorry, you go from 2 to the 20 down to 2 to the 18, and then you go down again to 2 to the 16, and like this you can go down, quickly. So
I see.
One
Thank
of
you,
audience
thank you.
has a question. I read it. Thank you. Is MPC-ITH approach also competitive for classical zero-knowledge application?
Well, this would depend a little bit by what you mean by classical ZK applications. In general, MPC-in-the-Head MPC-in-the-Head has a bit of like an upfront cost, because when you prepare the seeds for the parties, there's some you need to create some trees, you need to hash some things. So there's always a bit of a base cost that you have to. So it's not going to be, for example, if you want to prove knowledge of discrete logarithm, the traditional Sigma protocol is always going to be faster because you don't have all of this. And you don't need to repeat because it already has a soundness error that's quite high or quite low if you have a big group. So in the applications that have very efficient Sigma protocols already, MPC-in-the-Head is not going to replace that. But for applications where you want, for example, to prove, pre-image of SHA-256 hash function or these kind of things, these are not simple arithmetic they're not simple mathematical relations. And so here, MPC-in-the-Head has an advantage because it's flexible and you can prove any binary or arithmetic relation that you want.
Okay, thank you. Is there any question?
Maybe since you have time and I don't see any questions, so I can ask one more, Ciprien.
Yes, we have time.
Go ahead, yeah.
If I understood correctly, so the goal is that you want to prove this batch of just multiplication gates because additions are free, linear secret sharing. So can we say that if we can come up with a different basically proof for this inner product compression that you have here in this slide, so there might be hope to improve this Limbo paper protocol basically by having more efficient proof for this batch inner product?
Yes, in some ways, if you can prove that quicker or more efficiently, it would improve the Limbo protocol. Absolutely. Also, I haven't mentioned some more recent developments in MPC-in-the-Head. There has actually been a comeback of a Shamir secret sharing based MPC-in-the-Head. People have managed to show that if you have a Shamir secret sharing, you can open things much cheaper.
Actually, I was thinking of something like that because here you use, let's say, full three-shot things, but if you use some robust, let's say, secret sharing, then you can even reconstruct with less opening rather than just full of them or something.
Yeah.
Like
So
that.
the thing is that when you use full threshold in the broadcast model, because what we say, right, you open n-1, but opening n-1 actually just translates to opening the seeds and opening the output of the hidden party. So it actually translates to open 1. So in order to be competitive with that, any change in the secret sharing scheme that you use has to give other advantages. So MPC-in-the-Head in full threshold has 1/n soundness error. But if you use I think I'm saying this from memory, so I might be saying this wrong, but if you use a threshold T Shamir sharing, you might have n choose 1/n choose T soundness error. So in this case, in opening Shamir shared views means you have to open more. You can't open just one. You might have to open 2 or 3. But because your soundness error changes, you have to repeat less. And so, because 1 over n choose 2, for example, is 1 over n squared, roughly, the order. And so because you repeat less, the extra cost of the opening is reduced by the less repetitions. So the difficult, well, the interesting and challenging part of designing MPC-in-the-Head schemes is now there's so many ideas around. We don't know which combination of which techniques will give the best results always, because there's so many different parameters to change. But I mean, it leaves a lot of room for very creative improvements. So if there's any way that the inner product compression can be done better, it will improve Limbo and other MPC-in-the-Head protocols for sure.
I get it. Thank you very much for your good explanation and great presentation.
Thank you.
Is there any question? It seems that not any question. There is no any question. Okay. Thank you, Ciprien, for your presentation. It is very useful for me, and thank you very much.
Thank you. Thank you again for the invitation and the organization. I was happy to speak.
Thank you very much.